Hi, my name is Sam Caldwell, and I'm here to talk to you about typed dataspace actors. The goal of this talk is to answer two questions. First, what is the dataspace model? And second, what extensions to the simply typed lambda calculus are needed for typed dataspace programming? So concurrent programming is hard. There are many ways to structure concurrent programs, so we've seen almost as many linguistic models arise, each with their own pluses and minuses. One particularly helpful idea is the isolation between components in the actor model. Unfortunately, isolation is in tension with another central need of concurrency, sharing knowledge. On the other hand, tuple spaces offer a view of knowledge in a concurrent system that lends itself to easier sharing. The dataspace model seeks to build upon these ideas and alleviate the tension between isolation of components and their need to share knowledge. So, what is the dataspace model? From 5,000 feet, it connects actors via a restricted tuple-space-style shared memory. The restrictions serve to decouple components and implement a publish-subscribe communication pattern for routing messages, but it's really best illustrated with an example. I'm going to imagine setting up a smart home lighting system in my apartment. Here I am with the components I need: a central control hub, networked lights, and presence sensors. The first thing I do is plug in the controller, which has a dataspace program running inside it. Here's a graphical depiction of that program. At the moment, there's a single actor representing the control system itself. I then start installing the lights. I've labeled the first L1. When I install a light, the system spawns an actor representing that light. That actor shares one piece of information in the dataspace announcing its presence. This takes the form of a tuple with the label light and an ID. We call these shared facts in dataspaces assertions because of their resemblance to logic programming. The hub actor uses these assertions for configuration and control purposes. For example, each time I install a new light, the system may prompt me to associate that light with a specific room. In order to facilitate this process, the hub actor subscribes to light presence information, which we see here. Now, the way to read this is question mark, meaning I am interested in assertions matching the following pattern. The pattern matches tuples with the label light and any value in the second slot, signified by star. With the subscription in place, the system will inform the hub actor of matching assertions. Each light I install after that makes a similar assertion. In order to control each light, the hub actor asserts a control signal. Here, it asserts that the control state for the light with identifier L1 should be off. Of course, in order to receive the control signal, the light actor needs its own subscription. It does so with an assertion of interest in controls matching its own identifier and any value. Another important element of dataspaces is the link between assertions and actors. If L1 burns out, for example, the corresponding actor will exit. When an actor exits for any reason, the system automatically removes each of its assertions. The hub actor's interest also subscribes it to these disappearances, yielding a corresponding routing event. This information allows the hub actor to withdraw its control for L1 and notify me to replace the bulb. Next, I install each presence sensor. I've labeled the first PS1. Like the lights, the system spawns an actor for each sensor. The actors make an assertion with a current sensor reading using the label present and their own identifier. The hub actor expresses interest in the reading of each sensor with a corresponding assertion. Now, to see how the program evolves, we tune in for a breaking update as I move from the couch to the kitchen for a snack. As a result, the present sensor PS1 updates its assertion from 0 to 1. The update represents a change to the set of assertions matching the hub's interests. This is the condition for the generation of an event in a dataspace. The routing mechanism sends a representation of this change to the hub actor, bringing us to the subject of how the hub actor processes such events. To this point, I've been talking about dataspaces as configurations of actors, but ignoring the internal behavior of such actors. The dataspace models each actor as a pure function, so we can think of them as just terms in a lambda calculus. The signature for each actor is a function consuming information on updates to assertions that match its subscriptions and producing instructions to be interpreted by the system. These instructions pertain to manipulating the actor's own assertions, spawning other actors, or terminating. In this case, the hub actor will produce an instruction manipulating its assertions, namely changing the control signal for L1 from off to on. In turn, this update is relevant to L1's interest in control signals, yielding another event. This is the typical pattern of communication for dataspace actors. And here we see the light now on. Up to now, everything has been going as planned. But let's imagine a different reality where, while developing my control software, I get mixed up by all the different ways of controlling a light. On-off states, brightness percentages, HSV, RGB, and many others. While programming the hub, I represent lights as being either off or at some percentage of maximum brightness. But while programming the light bulb actors, I use just on-off states. Now, when the hub actor tells L1 to turn on, it does so with a percentage. This percentage still matches L1's interest, once again generating a routing event. However, now when L1 processes the update, it encounters a type mismatch, with the potential of causing any number of unexpected or undesired behaviors. Well, where I'm from, we don't like runtime type errors. To prevent them, we could develop actors using a typed language. We would then also have the potential for type-based design, documentation, optimization, and so on. So what would a typed programming language for dataspace actors look like? Recall that dataspace actors are pure functions, letting us model them as terms in the lambda calculus. It's then natural to use the simply typed lambda calculus as a starting point for writing typed actors. The informal signatures for actors can then be modeled as an arrow type. This leaves us with needing to determine what extensions to SDLC and arrow types we need to reason about dataspace events, instructions, and actors. Let's go back to our example to illustrate how to design types to meet these goals. Here is the point where the hub actor controls L1 with a brightness percentage rather than an on-off flag, introducing a runtime type error. A type system must prevent this scenario from occurring. At the same time, it ought to allow instructions that update the control assertion using on-off flags. This situation calls for suitably fine-grained types to distinguish the two scenarios. This is our first extension to the simply typed lambda calculus, a reflection of the assertion language to the type level, allowing for precise descriptions of assertions. Types include the constructor for assertions of interest, the question mark, the star pattern, and tags such as light, control, and present. Using this type language, we can enumerate the different assertions the hub actor manipulates: interest in lights, on-off control signals, and interest in present sensor data. These form the basis of the instructions type for the hub actor. They also need to be combined in some way. True union types are convenient for this purpose and are the second extension to the simply typed lambda calculus we use to describe dataspace actors. Now, going back to the example, we can identify the types of assertions produced by each actor in the system. We see that the light actor L1 produces light ID assertions and subscribes to control signals, and similarly, PS1 shares its presence reading. Moreover, if we take the union of each of these, we get a picture of the types of assertions across our whole program. From this view, we can easily conclude that all light control assertions are in terms of on-off states rather than brightness percentages. So we now have a reasonable way to describe the instructions for each actor, but what about the events? Since events are also descriptions of assertions, it follows that their types are then going to look similar, meaning unions of assertion types. And recall that the hub actor is a typed lambda. When I write the term, I am free to assume a type of my choosing for the input, and then program the rest of the behavior according to that type. The responsibility of the type system then lies in ensuring my assumption is valid in the context of the larger program. To understand how this plays out, let's look again to our example. Here we are back at the moment when the hub actor processes a presence update event. Earlier, we saw the generation of this presence update event was due to a change in PS1's reading and a matching interest from the hub actor. At the type level, we recognize a similar match between the hub's type of interest and presence readings and the type of sensor data assertions. We can then conclude that such assertions are potential events for the hub actor. Looking back at the types, we notice another match for light assertions, so they are also potential events for the hub actor. The pattern here is the following rule. If an actor may express interest in a type of assertion, then its type of events must include any assertion that may match this interest. This process directly corresponds to the routing procedure performed at runtime in dataspaces. To generalize beyond this example, I'm going to replace each concrete type with a meta-variable. Our system checks each actor by first analyzing the instructions type for question mark prefix assertions, i.e. interests. We then cross-reference those interests with the type of all potential assertions in the dataspace, determining the types of potential matches. Finally, we ensure that the domain of the behavior function corresponds to this type. This loop of dependencies is our final addition to the simply typed lambda calculus. Fundamentally, this extension adds an understanding of how data moves between actors and databases to the type system. Here's a simplified type rule implementing this reasoning. To check an instruction that spawns an actor with a given behavior, we first ensure that behavior has an arrow type. The codomain of this arrow type is the type of instructions the actor may produce. From these instructions, we extract the pattern from every type representing an assertion of interest. Finally, we cross-reference these patterns with the provided type representing the entire dataspace to find all potential matches. These matching types are potential events for the actor, so must be included in the domain type of the arrow. Now to recap what we've seen, the dataspace model of concurrency seeks to tackle the tension between isolation of concurrent components and sharing knowledge among them using tuple space-inspired publish-subscribe communications. To extend the simply typed lambda calculus with types that allow us to capture the structure of database communication, we can first reflect the assertion language at the type level, second, combine different possible communications with unions, and third, perform type-level routing to understand which communications are possible. There are many things included in the paper that I didn't cover in this talk, such as our prototype implementation using the turnstile DSL, a discussion of the value of termination for dataspace actors, and a thorough semantics. The semantics allows typed STLC components to interoperate through an untyped substrate, the dataspace. We combine these untyped concurrent and typed sequential models and improve the soundness of this composition. You can find the paper from JFP Volume 30, August of 2020, and at the given link. Looking beyond this paper, the dataspace model is implemented as Syndicate, including extensions and libraries to several languages such as Racket and JavaScript. Our turnstile prototype adds types to Syndicate and Racket, while we are exploring designs for Syndicate and TypeScript that account for database communications. Now, rather than program database actors in the lambda calculus, we use a DSL oriented around assertion-based conversations. This opens the possibility for richer type structures. When we model actor behaviors as arrow types, we lose information about the relationships between assertions. Looking back at this diagram describing the hub actor, we analyze the entire right and left-hand sides of the arrow at once. Doing so loses track of the fact that it is interest in light assertions that leads to light events, and interest in presence data that yields presence events that in turn leads to control updates. Tracking these temporal relationships is the basis of ongoing work on behavioral types for database actors. Thank you very much and stay tuned.